Subsets and Venn diagrams. One way to visualize the relationships between sets is in the form of a Venn diagram. Venn diagrams were first introduced by British logician John Venn. These diagrams are used to help conceptualize relationships in many fields, including set theory, logic, probability, statistics, and computer science. A Venn diagram is a way to visualize the relationships between sets. In a Venn diagram, the sets are represented by circles or ovals contained within a rectangular region representing the universal set. And we label the universal set U, and we label each oval or circle with the letter of its set. Example 1 says the following Venn diagram represents the sets of S, T, and V within the universal set U. And U is X such that X is in the English alphabet. This little thing means it is in. It is inside, basically. So we're going to use the diagram to answer these questions. As you can see here, none of these overlap. So that means that none of these sets share any common letters. If there was another set here and they shared the letter B, then it would look like that. List the elements of the sets S, T, and V in roster form. So S would just be K, A, and S. You don't necessarily have to put them in order. T is T, M, J, and D. And V is E, C, and P. Then it asks for the cardinality of each. So there's 3 elements in S. In T, there are 4 elements and 3 elements in V. Find the complement of T. So the complement of T would be all the letters except the letters that are contained in T. T, J, M, and D. So T complement would look like this. A, B, C, not D, E, F, G, H, I, not J, K, L, M, nope, not M, N, O, P, Q, R, S, not T, U, V, W, X, Y, Z. And it asks, is S equal to V? No, S would not be equal to V because they don't contain the same elements. But it asks, is S equivalent to V? Yes, it is, because they both have a cardinality of 3. There's an increasing number of electric vehicles on the roads in the United States. The number of charging stations available for those cars varies from state to state. The states with the most public and private electric charging stations are California, Florida, Oregon, Texas, and Washington. So let U be all public and private electric charging stations in the United States. C represents the charging stations in California, F represents them in Florida, and O represents them in Oregon. T in Texas, and W in Washington. The following Venn diagram depicts the 5 states with the most electric charging stations. The cardinal number for each set is shown inside the appropriate oval. So instead of listing all 5,415 of them in here, they just put the cardinal number in the Venn diagram. And we're going to use it to answer some questions. Which state has the most electric charging stations? Looks like California. Which state has the second highest number? Texas. How many electric charging stations do the top 5 states have all together? You would add them all together. You can't just say that they're all 19,996 because that number includes everyone in the United States. So if there's some charging stations in North Carolina, that would be included, okay? But we only want the ones for these 5. So we would add the cardinal numbers for these 5 states. And in these top 5 states, there are 10,299 charging stations. How many charging stations are in the United States, but not in one of the top 5 states in the diagram? Well, that would be the cardinality of U minus that total that we just found. So 19,996 minus 10,299. So there's 9,697 charging stations in the United States that are not in the top 5. A subset. If A and B are sets, B is a subset of A if every element of B is also an element of A. So if we can call B a subset of A if all the elements of B are also included in A. Now there might be more in A, but B is a subset if it includes all those elements. And we write it like this. It's this little sideways U with a line underneath. B is a subset of A. And when we drew this diagram here, we can see that C, O, W, F, and T are all subsets of U. Example 3 says, let U be a student at State University. W is a student at State University majoring in computer science with a minor in business. And Y is a student at State University majoring in computer science. So U, which we draw as a rectangle, is your universal set of all the students. Then Y is all the students who major in computer science. But then some of those also major or minor in business. So that would be included inside of Y. When B is a subset of A, and A contains at least one element that's not contained in B, like in our previous example, there would be students who major in computer science but don't minor in business. And B is said to be a proper subset and is written just with the little sideways U. B is a proper subset of A. And a way you can think about it is it's properly contained. Let X be 1, 2, 3. List all the proper subsets of X. So all the proper subsets would be any subset that contains 1 or 2 or 3, but leaves one of the numbers in X, okay? So you could have 2 elements in your subset, or 1, or none. So one example would be the subset 1, 2. 1, 3 would be a subset, and 2, 3 would be a subset. With one element, there would just be 1, 2, or 3. Those are all subsets. And no elements would have to be the null set. The number of subsets and proper subsets of a set. If the cardinal number of a set is n, then there are 2 to the n subsets and 2 to the n minus 1 proper subsets of the set. So basically you're just talking about reorganizing your numbers here. So you can use all the elements of the set in your subset, or just part, and all kinds of organizations. But to be proper, you have to leave one of them, one of the letters in, or elements in the set. So that's why it's 2 to the n minus 1 for proper subsets. Dr. Williams is eating at China Buffet one afternoon and notices a sign that says, "So many possibilities. You could spend a lifetime eating at China Buffet and never having the same meal twice." He wonders how many different plates he could make from the 16 items on the buffet. He can have all, none, or some of the items. Help Dr. Williams determine the number of different plates he could make at the buffet. So we're just choosing a subset because he could have all of them. So we're going to use the formula that the number of plates would be 2 to the n, or in this case, 16. So there's 65,536 different plates that he could make. And that concludes this section.